Class and welcome everyone. So this is design of steel structures. I'm Engineer Ronjan Argami. So today we are going to have supplementary problems on effective area and staggered fasteners. So let us say we have here a problem in SI units. So determine the actual effective net area of the 10 by 200 millimeter plate for the butt joint connection shown if the diameter of bolt is 20 millimeters. So use reduction factor U is equal to 0.85. So in here we do not bother ourselves in the calculation because reduction factor is already identified or given. So here's the illustration. We have a lap or a butt connection between the 6 millimeter by 200 millimeter plate, and the central plate is 10 millimeter by 200 millimeter plate. So this is the side view. So the arrangement of the bolt is on a symmetrical configuration wherein the width is 200 millimeters. So in here, I would like to show you this nominal hole dimension table for bolts in SI units. Of course, what we did last time is to add 1/8 to our diameter. So in some books, we can find that the calculation is based from the standard diameter. Okay, so meaning the 20 millimeter diameter shall have a standard diameter of 21, and then all we have to do is to add 1.6 millimeters to that standard diameter of that bolt. So we can see that in this table provided by the National Structural Code of the Philippines 15th edition. So in this case, if we have 20 millimeter diameter, the standard diameter is 21, we add 1.6, so we'll arrive at 22.6 millimeter effective hole width of your bolt. So going back to this problem, knowing that our diameter is 22.6 because that is included in the calculation of the net area. We can now use this formula. The net area is equal to the gross area minus the summation of the thickness times d prime, and that d prime is given by the expression diameter minus s squared all over 4g, wherein s here is the pitch formed by staggered connection and g is the gauge distance. Okay. So the net area in this case is equal to, of course, we just multiply. This is a plate, the width by its thickness, and then we less the thickness of the web or the thickness of the plate, 10. So in this case, we do not have a pitch distance because there is no staggered connection. So all we need is to multiply your diameter, nominal diameter as calculated. So there are two of them, so we just have to multiply 2 on that reduction of area. So therefore, the net area will be equal to 1,548 square millimeters. So of course, for the effective area, so we have to multiply your net area with the reduction factor. So it was already given, so we'll just have to multiply that by 0.85. So it will yield to 1,315.8 square millimeters. Okay, so that's it for this problem. So the calculation of that one is actually for fracture. wherein we can also consider the effective area for your yielding. Of course, when we talk of yielding, we use the gross area. So the gross area multiplied by the way, the gross area is 200 by 10 times 0.85, then the effective area is equal to 1,700. So these are the effective area for fracture and for yielding. So normally, if we consider calculations on the safe allowable load, we consider the least value among this area. Okay. So next problem, compute the net area of the riveted connection shown if the thickness of the plate is 12 millimeters. So in here, the rivet diameter is equal to 20 millimeters. So here is the view given the dimensions. Of course, obviously there will be staggered distances because we have unsymmetrical arrangement of your bolt. Okay, so given all of those dimensions, so first things first, of course, the calculation of the area of the nominal hole dimensions of your bolt. So that is 21. As usual, we are going to add 1.6 if it is in terms of millimeters. Okay, so we arrive at 22.6 once again. Okay, so next is to draw your root following the staggered connections, and then of course we're going to label the points on that root. So obviously this is one root A, B, C, D, E. So we apply this formula that the net area is equal to gross minus thickness times D prime, the summation of those product. So we start calculation, of course, on the bolt from top to bottom, following your direction of your root. So in this case, the location of the first bolt is on B. On B, there will be no pitch yet, or S dimension. Okay, so of course, the first term here is the gross area, 300 by 12. So 12 is the thickness of our plate, 300 is the width, less the thickness of your plate, multiplied by this D prime, 22.6 minus S squared all over 4G. So in this case, there will be no value for that, and because came from your A, so there is no pitch yet from B to A. And then next we proceed to the next bolt. Next to B is C. So here C, you can see that B is having a pitch of 50 plus 25. Okay, and a gauge distance of 100. So replace that one, multiplied by your thickness, 12 millimeters. So moving on to the next bolt, we have bolt D. So prior to D is C. All we have to do is to look at the pitch distance, S is equal to 25, and we also have the gauge distance of 75 millimeters. Now we place that equation multiplied by our thickness 12. Okay, so if you notice, S squared is 25 squared, your G is 75. So now that we have already gone through with the bolts we just have to compute for the net area, 2,980.15 square millimeter. Now, considering another root here, we can consider ABDE. Say this is ABDE. So we do the same procedure. Start from top to bottom. In this case, we start at B. We're in the AG, as usual, 300 by 12 minus the thickness times D prime. So this is the thickness. The D prime, we take note that there will be no pitch yet here, okay, because there is no diagonal distance yet, or horizontal distance from A coming from B. Okay. So next we proceed to bolt D. Okay, so this is bolt D. So we take a look at the bolt prior to B. So using that new root, of course, we have negative 12. So it came from B. Therefore, there will be a pitch of 50 here and a gauge distance of 175. So the distance between B to B vertically. So that will be placed in our equation involving D prime. Hence, we have completed already for that root ABDE. Therefore, we can compute for the net area to be equal to 3,100.46 square millimeter. So between this calculated or derived net area, we'll consider the least value. Okay. So next, moving on to the next problem, we have compute the area net of the 150 by 100 by 12 mm angular section with 20 millimeter diameter rivets. Once again, the property is given, especially the area of the angular section is 3064 millimeters squared. So in here, we are going to use this illustration. Of course, we can observe that in the connection of this angle section, there are connections on two elements. Of course, because this is bended, the angular section is bended, there are connections on the horizontal element and the vertical element of this angular section. So, just like what was introduced last time about the calculation of the gauge distance, all we need is to label or get the distance of your bolt to the nearest corner, and that say that is G1, okay? So in this case, that is 56.25. Likewise, for the other element, you get the distance of the corner up to the center of your bolt or your nearest connection, say G2. Okay? In this case, we have 62.5. Now, knowing that one, we imagine to bend this angular section at this point. Okay? So we can see we unfold it, or we actually fold it to be parallel to the web member. Okay, so when we do that, of course, we will be needing this distance. Say that gauge distance is the sum of your G1 and G2, V less the thickness. Okay, so you just have to perform that. 56.25 plus 62.5 minus 12 mm as its thickness. So in here, come up with 106.75 millimeters, because this will be needed in the calculation of your D prime in a while. So completing the dimensions, we have an equal distances here, 75 millimeter. So for our D, 20 mm, so the size, the actual size is 21, and then we just add 1.6. So we come up with 22.6 once again. And then we label possible root here. So we have your ABC. So we consider the first root A to C. So A to C has no staggered distance or staggered configuration. So again, this is the formula. Starting at A, of course, we consider first the area of the angular section, 3064 millimeters squared. Next is multiply your thickness by this D prime. In this case, there will be no pitch distance since we have a parallel configuration from A to C. Okay. Likewise, for C, coming from A, there will be no pitch distance. So that is set to 0. Hence, we can compute for the area of root AC to be equal to 2521.6 square millimeter. So, in this case, we are going to have another root, say ABC. So at root ABC, obviously, there will be a pitch distances, okay, connection between A to B and B to C. So let's do it. So for the net area, 3064. By the way, do not be confused, because 3064 is already an area. So we do not need to multiply any thickness because that is already an area. So first we have the bolt at A. There will be no pitch distance. So minus the thickness times D prime. Okay, so this expression is cancelled. So moving on to the bolt B. Coming from A, there will be a pitch distance 75 millimeter and a gauge distance of 62.5. So that shall be multiplied to your thickness and incorporated in the calculation of your D prime. Okay. So next we have bolt at C coming from D. There will be a pitch distance of 75 and a gauge distance of 106.75 millimeter. So in that case, so this is the thickness times D prime, 22.6 minus 75 squared, the pitch distance between B and C, with the gauge distance of 106.75 millimeters. So in here we can now compute for the net area of root ABC. So among the derived net area, of course, we're going to consider the net area with lesser value, 2521.6 millimeters squared. So moving on to the next problem. So here we have the miscellaneous channel MC300 by 67 is bolted as shown on the figure by 20 millimeter diameter bolts. A36 steel is used with Fy is equal to 248 megapascal. and Fu is equal to 400 megapascal. To recall, Fy is used for yielding and Fu is used for fracture. So the requirement, letter A, compute the area net of the channel section. The second requirement is to compute the effective net area of the channel section using the alternative calculation. So letter C, compute the allowable tensile strength of the channel. So here's the illustration. So in this channel, all of the reinforcement or connections can be found on the web, but no connections on the element of your flanges. So given all of these dimensions and its properties, we can now designate a root here. Of course, we have the properties, the area, the depth, the web thickness, the flange thickness, and the width of the flange. Okay, so we'll compute the net area of the channel section. We're going to lay down of the bolts ABC. Starting at 8, there will be no pitch yet. Of course, we place first the gross area, the first term in the equation, and then we less the thickness multiplied by the d prime. So in the 2.6 minus s squared all over 4g. S here is 0. No pitch distance. Okay. Next, moving on to point B. So point B, we just have to observe the bolt on top of point B. Say we have A. Of course, there will be now pitch distance 50 millimeters. Likewise, we also have a gauge distance in millimeters, 87.5. So we place our equation, multiplied by 17.8. By the way, 17.8 is the web thickness. Again, because your connection can be found in your web. Okay. So multiply by d prime. D prime is d minus s squared all over 4g. So we already identified the s and gauge distance. Okay, moving on to the bolt C. Okay, so bolt C coming from bolt B. Of course, again, we have the pitch 50, the gauge distance 87.5. So we just place that into our equation. 50 squared all over 4 times 87.5. Okay, so moving on to bolt C, we have those values of S and the gauge distance. So again, we place that in to our equation. So I think that should be the last bolt to be considered. Therefore, the net area can be calculated, and we build to 7,297.45 square millimeters. Letter B. Compute the effective net area of the channel section using alternative calculation. So on the alternative calculation, all we have to do is to multiply a reduction factor to your net area. So for bolted connection, of course, we're going to use the net area, while for welded connection, we're going to use the gross area. In this case, we're using the net area multiplied by your reduction factor U. So as an alternative method, of course, we just have to take note of these provisions here, that instead of using this formula, that U is equal to 1 minus x bar all over L, for W, M, S, HP, or T cut from these shapes, like structural T or split T. Of course, this provision shall be applicable on our problem. Connection through the web with 4 or more fasteners in the direction of loading. we use a reduction factor of 0.7. So again, your web or your connection shall be located on the web. So it satisfies these provisions. Unlike the first two provisions here, that the connection shall be found in the flanges. Obviously, our connection here is on the web. Therefore, our U factor will just be equal to 0.7. Hence, that shall be multiplied to our net area, 7,297.45. So in that case, we arrive at 5,108.22 square millimeter. Okay? So letter C. Compute the allowable tensile strength of the channel. So once we have known all of the net area on yielding and for fracture. First, for yielding, of course, FYAG is the formula for P sub n, or the allowable load. We have 248 times 8,250. So in here we can yield this to 2,046 or 2,046,000 newtons, and this will be equivalent to 2,046 kilonewton. Now, to compute for the allowable loading by the effect of yielding, of course, you just have to multiply 0.6 on FYAG. So we do that and we'll come up with 1,227.6 kilonewtons. So moving on to fracture, the effects of fracture is given by the equation by Fu all over the effective net area. So in that case, we'll just have to substitute the values, and the derived effective area is equal to 5,108.22 millimeters squared. So therefore, the net load will be equal to 2,043,288 or 2,043,288, which is equivalent to 2,043 kilonewtons. So this time we are going to have the 0.5 to be multiplied to FUAE. Actually, that is FUAE. And 0.5 of 2,043 is equal to 1,021.64 kilonewtons. So at this point, we are going to choose the list value of the derived allowable loading. Actually, this is using the alternative strength design or ASD method. So moving on to the next problem. So in here we have the plate that shall be connected by a 34 millimeter diameter bolt. So assume that the diameter of holes is 2 millimeter larger to the bolt diameter. So the A36 steel section has a properties of Fy248 and Fu of 400 megapascal. So for the first requirement, compute the nearest value of the width B so that the net width of the bolt along the route 1, 2, 3, 4 is equal to the net width of the bolts for that of 1, 2, 4. Then the second requirement will be compute the effective net area for the tension in plates. And finally, compute the value of P so that allowable stress shall not be. So here is the illustration of P. P here is parallel to your member. So we have all the dimensions are given here. B is a variable. So if this is B, therefore this is 150 minus B. The thickness is given. The width is given and an equal configuration along the width of your plate. So first things first, we're going to label all our bolt here and then illustrate a route. Say the route is 1, 2, 3, 4. And for that route, of course, we start from top to bottom. So in here, we're going to work with the net width instead of the net area, since we must have to adhere to the first unknown, or the condition of the first unknown, that the net width of the bolts along 1, 2, 3, 4 shall be equal to the net width of the bolts along 1, 2, 4. So again, we work with the net width, and then later on we're gonna multiply it by the thickness to make it as our net area. So the net width is obviously 400. We place that one, and then this is the diameter. So 34 is the diameter, and then our assumption is that the holes is 2 millimeter larger the bolt diameter. And when we test this expression, at this point we do not have that term because there's no pitch yet. Okay, so next, moving on to the second bolt, coming from the first bolt, there will be a pitch of 60 and there should be a gauge distance of 100 millimeters. Once again, we place or we deduct the difference between your diameter and that expression S squared all over 4G. Okay, so we have mentioned the values of S and G. We have 60 and 100. Next, the third bolt coming from second bolt, of course, we'll be having a pitch distance of B and a gauge distance of 100. So again, we place the equation. So next is the fourth bolt coming from the third bolt. Okay, so we have a pitch distance of 150 and a gauge distance of 100. So once again, we place that in the calculation of D prime. Okay. So all of the bolts were included in the equation, so we can now compute for the net width, and the net width is equal to 321.25 millimeters minus B squared all over 400. So this is actually the net width for that route 1, 2, 3, 4. Okay, so we consider another route, say 1, 2, 4. So first, the first bolt, of course, that has no pitch spacing. And then for the second bolt, say number 2, coming from 1, there will be a pitch spacing of 60 and a gauge distance of 100. So we place that into our D prime equation, 60 and 100. And then for the fourth, connecting from 2, there will be a pitch distance of 150 minus B with a gauge distance of 200. So we place that into the D prime equation. So 34 plus 2 minus 150 minus B squared all over 4 times 200. So therefore, our net width on route 1, 2, 4 is 301 plus 150 minus B squared all over 800. So this time, now that we have all of the net width of the routes, okay, Then we just follow the condition of letter A, that equation 1, 2, 3, 4, the width of that is equal to the width of root 1, 2, 4, this one, okay, and that one. So just place this equation and equate it to that equation, okay. So solve for B. So in here, we'll arrive at 20.25 by having 301 to be transposed on the left hand side of our equation. We add this term and just place what is left on the right hand side of the equation. And this one shall be transposed the right portion of the equation to be combined with the variable. And in here we shall get the LCD, or the least common denominator, of 800. So the first term, 2b squared, is derived by 800 divided by 400, that is 2, multiplied by b squared, and that will be b squared, and that shall become negative 2b squared. Okay, so for the second term, you just have to copy the numerator, since 800 is also the denominator of that second term. Okay, so this is equal to 20.25. So by cross multiplication, we are going to have 16,200, and just place what is left on the left hand side of the equation. And then in here, we shall expand that 1 with it to 16,200, and then it expanded further, okay, let it be combined to negative 2b squared and equal to 16,200. So finally, we transpose this constant to the other side to combine it to 22,500. Then we will have an equation equal to 6,300 minus 300b minus b squared. So this is equal to 0. So we calculate by quadratic formula, and then we can get the root of b is equal to 19.71 millimeters. So having that, we can already substitute it in here so that we can calculate the width for the root 1, 2, 3, 4. And obviously, class, that is also equal to root 1, 2, 4. Now, we haven't yet explored this root. Who knows that root 1, 2, 3, 5 may be smaller to what we have derived, 322.22 millimeters. So using that root, of course, we again write the equation. First the gross width of 400, and then less the first bolt of 1. Okay, so bolt 1 has no pitch yet. And moving on to the bolt 2, of course, we have a pitch distance of 60 and a gauge distance of 100 coming from your first bolt. And then moving on to the third bolt, of course, we have a pitch of 19.71. So what we have just computed is the value of B, actually, and a gauge distance of 100. By that, we arrive at 301.97 millimeters. So it is really smaller than what we have computed or considered in the calculation. The roots 1, 2, 3, 4 and 1, 2, 4 has a net width of 322.22, while the new root of 1, 2, 3, 5 will be having a net width of 301.97. So therefore, this shall now be considered in the calculation of the net area. So the net area is equal to the thickness times the net width. The net area be considered as the list multiplied by the 12 thickness of the plate. We have 3,623.64 square millimeter. Now that it's already known, we'll just have to compute for the nominal load FYAG for yielding, and that is 248 times 400 by 12. We arrive at 1,190,400 newtons, and that will be equal to 1,190.4 kilonewton. Now for the allowable loading using ASD, we just have to multiply 0.6 to that, P sub n. So therefore, we arrive P sub n allowable is equal to 740.24 kilonewtons. And for fracture, Pn is FUAE, okay, 400 by 3,623.64. So we have 1,456 Newton. So in the allowable loading, we just have to multiply 0.5 on FUAE. So finally, the allowable Pn is equal to 724.73. So therefore, the allowable Pn is the least among these derived allowables. So that ends our session for today. Thank you for listening and see you next time.